Welcome back to the video series on integration and differential equations. In this video, we're going to look at an application of constant coefficient DEs. In particular, we're going to look at spring mass systems. So let's imagine that a spring with a mass attached is fixed to the ceiling. So here's our mass at the bottom here. Here's our spring, it's fixed to the ceiling. And the position where the mass comes to rest, this position here, we're going to call the equilibrium position. Now let's say our equilibrium position is here. And let's say we pull our mass from equilibrium, we pull it straight down past our equilibrium position and we let go. Then our mass is going to move vertically. We might get this type of motion, and our ultimate goal is to try to describe the motion of our mass. We'll let x represent the displacement of the mass from equilibrium position in meters. This is a vertical displacement, and despite the fact that it's a vertical displacement, it's still really common to call this x rather than y. So we'll stick with that convention. Let's come up with a coordinate system for x. We're going to let the equilibrium position be represented by x equals 0. And then from there we're going to let the downwards direction be positive and the upwards direction be negative. The reason we take the downwards direction to be positive is because acceleration due to gravity is downwards. Our goal in working with any spring mass system is to find a function x of t, which gives the displacement x after t seconds. So in other words, we want to try to describe displacement in terms of time. Now let's see if we can come up with a dE that describes the motion of the mass. So let's recall, if x represents displacement, let's think about what the first two derivatives of x represent. So we'll talk about x prime and x double prime. X here is a function of t. So when we say x prime, we mean the derivative of x with respect to t. Okay, so just a derivative of displacement with respect to time, that's going to give us velocity. And if we take the second derivative, we get acceleration. So this will be very helpful when we go to set up our dE describing our spring mass system. So here's what our dE looks like. We will have mx double prime equal to negative bx prime minus kx plus f of t. And I'm going to mention here that m, b, and k are all constants. So let's try to look at the physics behind this differential equation. I think if we can understand what all the terms represent, then it should be fairly easy conceptually to understand this dE as a whole and to remember it really easily. So this term on the left side, this is mass times acceleration. In other words, this is describing the net force acting on the mass. Moving over to the right side, this minus bx prime, this is damping, a damping term. You could think of that as air resistance, for example. So physically, damping is going to be proportional to velocity, and it's going to be in the opposite direction. So the faster the mass is moving, the more damping it's going to experience, and the damping is acting in the opposite direction of the motion of the mass. So in brackets here, let's just write, for example, air resistance or any sort of fluid resistance. So looking at this symbol then, the B, this is our damping constant, and the negative is just representing the fact that it's acting in the opposite direction of the motion. All right, let's next move to this negative kx term. This might be familiar to you from Hooke's law. So this is the restoring force exerted by the spring. And that acts in the opposite direction of displacement. So symbolically, x is our displacement here, k is what's called the spring constant, and the negative is indicating that this force is acting in the opposite direction of displacement. Finally, f of t here, this represents any external force that's applied to the system. In most examples, this external force will be 0, but I include it here just so that we can have a comprehensive discussion. So now, reading this symbolically, we'd say, well, mass times acceleration is equal to the damping force plus the restoring force exerted by the spring plus any external force that's applied to the system. So one thing you might wonder here is why there's no gravity term in this dE. Let's remember that we're working with respect to the equilibrium position, and the equilibrium position is defined as the position where the mass comes to rest. So at this point, the restoring force exerted by the spring, which is acting upwards, and the force due to gravity, which is acting downwards, those two forces balance there. And because they're balancing, we don't need to take gravity into account. So this is why it's really convenient to work with respect to the equilibrium position as opposed to, say, working with respect to the natural length of the spring. So much more convenient to work with respect to the equilibrium position because we've already essentially taken gravity into account. Here's the example we're going to work through. A 9.8 Newton weight stretches a spring 2.45 meters. There's a damping force numerically equal to twice the velocity. The mass is pulled 20 centimeters below the equilibrium position and released. We want to find the equation of motion. First thing let's try to write down our dE by thinking conceptually. So we've got mass times acceleration, which represents our net force, and then let's think about the three different forces that could be acting here. So we could have our damping force, so that's going to be proportional to velocity and in the opposite direction. So we'll say negative bx prime, b is just a constant here. Then we've got our Hooke's law force, so minus kx. So that's proportional to displacement, and it's negative again because it's acting in the opposite direction of displacement. And then we'll say plus f of t, just in case there's any external force applied to the system. Okay, so now m, b, and k are constants. Let's see if we can figure out their values. So let's start with mass. So mass is going to be 9.8 newtons divided by 9.8 meters per second squared gives us a mass of 1 kilogram. Excellent. Okay, now let's think about our damping term here, or you could call that the air resistance or fluid resistance term. So let's think about this B. We're told in the question there's a damping force numerically equal to twice the velocity. Okay, so what that's telling us is that numerically B is equal to 2. Okay, so it's giving us the you could say the absolute value of the constant. But let's think about the units here. So this damping is a force, so we should really say it's 2 newtons per meter per second. so that when b is multiplied with velocity, we get back to units of newtons. And remember that this term here is going to be negative because the damping force is going to be acting in the opposite direction of our velocity. Okay, now let's think about k here. According to Hooke's law, F equals kx. We're told that we've got a 9.8 Newton weight, so that's our force there. K is unknown, and our displacement x, we're told that that weight stretches the spring by 2.45 meters. Okay, so solving for k then, if we divide 9.8 by 2.45, we get 4. So the units here are newtons per meter, and that's our spring constant there. Right, there's no mention of external force in this problem, so the external force here is going to be 0. So let's write down a cleaner version of this dE. I'm going to drop the units here. Mass measured in kilograms is 1. So I'm going to write 1 x double prime, or even better, just write x double prime is equal to negative 2 x prime minus 4x, and that last term is 0. Okay, so that is our dE. And although we haven't written the units down, we did check over here that we've got the correct units because all the terms here are expressed in newtons. Great. So now let's think about our initial conditions. We're told that the mass is pulled 20 centimeters below the equilibrium position and released. So remember in our previous discussion we said that the equilibrium position is going to represent x equals 0, or be represented by x equals 0, and that the downwards direction is going to be considered positive because gravity acts downwards. So if the mass is initially starting 20 centimeters below equilibrium position, then we're saying the position of the mass at time 0, x of 0, is equal to, it's going to be something positive, and we want to represent this as 20 centimeters. Well, remember that x is measured in meters, so really the correct thing to write here would be 0.2 meters. Okay, so the units are important here. Often you will have to make a conversion from centimeters to meters in writing down these initial conditions. So now let's think about our initial velocity. So our velocity at time 0 is, let's see, well, we're told that the mass is released, so meaning initial velocity 0 meters per second. So there we go. We've got our dE right up here. We've got our initial conditions, 2 initial conditions because it's a second order dE. And from here on out, it's just going to feel like a constant coefficient dE like we saw in some of our previous videos. So I've just recopied the dE and the initial conditions, and let's go about finding the equation of motion.